this is an outline. So I will introduce the differential form of the Maxwell equations. And in between, I will also introduce two theorems. The first one is called the divergence theorem, or you can also call it the Gauss theorem. So you know two of the laws in the Maxwell equation are called the Gauss law. So that one should be related to the Gauss law. So the Gauss theorem should be related to the Gauss law. Also, we have the Stokes theorem. And yeah, you can simply also imagine that the Stokes theorem should be related to Faraday's law and also the Ampere's law. And finally, I will also talk about the conservation of charge, because in chapter 29, you know, we have the Ampere's law, but without the displacement current. And in chapter 32, you know that law called Maxwell's law. It tells you that the line integral of the magnetic field equals to the mu naught multiplied by the displacement current. And finally, it tells you that the right-hand side should be added together to form the whole Ampere-Maxwell's law, or usually I just call it the Ampere's law for the whole law. Yeah, actually, if the Maxwell equation need to satisfy the conservation of charge, then the Ampere's law need to have two terms on the right-hand side. Because if you don't really consider the conservation of charge, you may consider, if we have the static current and also the displacement current, how about if there are some other else current which should be included? The answer is no if we really consider the conservation of charge. And you see why the Maxwell equation at this stage would satisfy the conservation of charge. So up till now, here we can see the Maxwell equation, and it is called the integral form because on the left-hand side, we can see for the two Gauss law, we have a surface integral on the left side. And for the Faraday's law and Ampere's law, we have the line integral on the left side. Yeah, the right-hand side, we have something different, Q enclosed, the time derivative of the magnetic flux, and also this one is the current plus the displacement current. But anyway, on the left-hand side, we can see the different types of the integral. So we will call this for equation the integral form of the Maxwell equation. And of course, in this sense, we should also have the differential form for the Maxwell equations. And I'll let you know how to derive the differential form of the Maxwell equation from the integral form. Okay, so here, originally, we will simply write the magnetic flux or the electric flux simply by this notation, the phi b and also phi e. But generally, if the magnetic field or the electric field are not uniform over the space or over the surface of the Ampere loop, because for this case, we have a curvature. Let's say C here, like this, maybe like this. Then phi b here should concern the surface, which is enclosed by this part. It doesn't necessary to be a plane, or it doesn't necessary to a plane. It can be a curvature, maybe something like this. I don't know how to draw it properly, but it can be a curvature. It can be a curvature. The only constraint is that this surface should be bounded by this part. Okay, so generally, this phi b can be written as the surface integral of b dot dA, and this a is bounded by this curve. So here we can actually write it like this, and also the electric flux can also be written as the surface integral of the electric field. We know that these two integral is not a closed surface integral, so we don't have a circle here. But for these four, these are for the Gaussian surface, which is for a closed surface. So we have a circle here to represent the closed surface integral. And also for these two line integral, we have a closed path. So we have a circle here to represent the closed surface, closed line integral. So these are closed surface integral. So this is for a closed line integral. So in mathematics textbook, usually we will rather write it as this one should be like this. So you use two integral sign to represent surface integral to avoid misunderstanding, because this one and this one are actually the same, but in this textbook it only use one to represent, this is a Gaussian surface integral. And of course for this one, it can be written as this way. And so as this one can be written as something like this. But in order to match with their notation, with the textbook, I just use one integral sign here. And furthermore, we can also rewritten the Q enclosed with a triple integral in terms of the charge density. So this rho is called the charge density. Actually, we have used this notation before when we learned the electric field around chapter 22, 23, somewhere right there. We have used this notation before. So here we can also rewrite Q enclosed to be a triple integral of the charge density. If the charge density is not uniform, we really need this triple integral. So it is like you try to separate the space into 3 dimensions, and then for each small dV, we will assume that the rho is uniform in a very, very small spaces. So we can multiply this density by the V, and then we add all of them together so that it is the total charge amount. So it's like the density multiplied by the volume, and then we add all of them together, and it will be the total charge amount. And also likewise, this is the current. Originally, this is the current enclosed by this path. And actually, the current can also be written as the surface integration of the current density. So this J is current density. So originally, when we learn in the textbook, the Maxwell equation is like this 1, 2, 3, 4 equation. So it looks pretty nice. It looks pretty nice. So we try to shrink all the notation to be a variable only. But if we really want to generalize this one, we will rewrite this Q, phi B, phi E, and also the I into different integral. So as you can see here, we have a surface integral here and equals to another triple integral. So of course, this one is simpler because we only have a 0 on the right-hand side. And for this one, this is a line integral equals to a derivative of the double integral, a surface integral. And this line integral equals to this double integral plus a derivative of another double integral. So yeah, we try to expand the notation like this. So the next step, yeah, so actually the differential form for the Maxwell equation will be like this 1, 2, 3, 4. So this is the Gauss law. This is the Gauss law for the electricity. This is the Gauss law for the magnetism. We have this notation for the divergence. The divergence of E equals the charge density over the epsilon naught. And then the divergence of the magnetic field is 0. And yeah, so this is called the curl. The curl of E is negative, partial derivative of the magnetic field. And also the curl of B is mu naught multiplied by the charge density plus epsilon naught times the partial derivative of the electric field. So in this case, we have EB to be unknown vector. Usually, if we need to use the differential form for the Maxwell equation, we would definitely like to solve the E field and B field in terms of different distribution of the charge and also the distribution of the current density. So in this case, given a rho, which is a field, and the other vector field, which is the current density, then we would like to solve E and B. And actually, you know that EB are vector field, which means that when you given E of x, y, z, then for every point there will be something like EX times I plus EY. It should be something like EX of x, y, z times I plus EY of x, y, z J plus EZ x, y, z times K hat. So even for this E, there should be like 1, 2, 3. 1, 2, 3 unknown in 3 dimensions. It's the B would be something like this. So it would be like BXYZ equals BX XYZ in the x dimension, x axis, plus BY XYZ J plus BZ XYZ K, something like this. So when we usually do some calculation in the textbook, it should be like when we try to fix only one point or only one axis in the space, and we try to find the B in one dimension. So suppose the distribution is symmetric in some sense, then the calculation will be simpler. But generally, solving E field and B field could be quite complicated because you can see we have XYZ, and then we also have the XYZ component for the E field and also B field. So the unknown function are quite complicated there. Yeah, you can see. This is an unknown vector in 3 dimensions. But actually, the differential form of the Maxwell equation will be more useful when we will try to use the numerical method to solve the E field and B field for the given charge density and current density. So here, when we try to compare the corresponding integral form and the differential form, so the Gauss law is like we have E, the surface integral, equal this one, and then this surface integral corresponds to this one. So it's like we have the surface integral here, and we change it to the divergence, and we can simply skip this triple integral on the right side. So you can see rho over epsilon naught. Of course, this is 0, so this side is also 0. And for the Faraday's law and Ampere's law, you can see this is line integral. So we change it to the curl of E, curl of B on the left side. And for the right side, we have the derivative. So we change it to the partial derivative. Yeah, I still forgot. Yes, here we still should have T here. So when we really need to solve some dynamic system, so it will be even more complicated. There are even more one more dimension. Yeah. So here you can see we have a time derivative here. So you can see here we just skip through this double integral. So with the time derivative of the B field, and here we skip through this double integral. So we have mu 0j epsilon naught partial derivative of E mu 0 partial epsilon naught times. Yeah. So it's just simply like as much as we change the left-hand side integral to be like this curl and this is divergent and the curl. Then on the right-hand side, we can just skip through all the integration on the right-hand side. So let's see how we can do this thing more rigorously. So here is the gradient operator. You should have seen it in chapter 24. At that time, we know that E is actually minus gradient V at that time, if you still remember. So E is the vector field, and at that time we told you that I told you that V is the scalar field, so it will be easier to find because as much as you have many sources to generate electric potential, then you can just add all of them together, and you only need the scalar sum to add all of them together, which is the integral. But yeah, for the scalar sum, it will be easier. You don't need to decompose it different component, XYZ component, and then you integrate individually. Here we only need to calculate the overall V, and then we take the divergence. Then we can get back the electric field. Because if you directly calculate the electric field, you need to calculate the x-axis component independently, and then you add them together. So you get the overall x-axis component, and then for y-axis component and z-axis component. So you need to repeat it 3 times. So probably calculating the potential first will be easier, and then take the gradient. In Cartesian coordinate, it will be nothing like this one. So this is called the gradient operator. It will not appear individually. This gradient operator is like you add this gradient to some other vector field or some scalar field. It depends on how do you use it. So actually, for the gradient operator, you can operate to the scalar field, which is in this case is potential, electric potential. So we will have partial x v in the I direction, and then plus partial v partial y in the y direction, and plus partial v partial z in k dimension. In z direction. but actually we can just write it individually. So this is called the operator. It can operate to something else, which is usually a scalar field. So in previous page, you know that we are not only have the gradient operator, we have a dot here and also have a cross here. So actually, this is actually the dot product and the cross product. So it is like you have the gradient operator, have the inner product with a vector field, have a great inner product with the vector field. So it is like for a vector field f, which is written as f of x times I hat plus f of f sub y j hat plus f sub z k hat. So this f is decomposed in x, y, z component, of course, in the Cartesian coordinate. So the divergence of f vector can be written as partial fx partial x plus partial fy partial y plus partial fz partial z. So it is like gradient of gradient dot f, which is usually we'll call it a divergence of f. Some textbook will write it like this, but I used to write it like this. With the gradient dot is f. So it is like partial x I hat plus partial y j hat plus partial z k hat dot with fx I hat plus fy j hat plus fz k hat. So when you try to calculate the inner product, it is like you have this one multiplied with this one. So this is partial fx partial x. And this one act with this one, I dot j will be nothing but 0. So we don't have I dot j, I dot k. I dot j, I dot k will also be 0. So we only have j dot j, which is 1. So we have plus partial fx, partial fy, partial y. And then we still have this third term, which is a partial fc, partial z. Partial fc, partial z. Yeah, something like this, which is actually this one. In the Cartesian domain, all this operation will be easier to imagine. In other coordinate, it will be even more complicated. Yeah, so this is the divergence operator. And and actually the physical meaning of the divergence is like if, of course, f is a vector field. If divergence of f is larger than 0 at some point, for example, at this point, which means that this vector field are flowing outward. If gradient of f is smaller than 0 at this point, which means that the f should be pointing towards the point. And if a gradient dot f is actually 0, which means that you cannot see whether the vector field is flowing in or flowing out at that point. It can be something like this, going upside or downside, going upward or downward, equally distributed, or maybe f is actually 0. It can also be okay. So, but you cannot clearly see that whether the f is going inward or outward at any point. So this is the physical meaning. And another operation is called a curl. It's called a curl, which is like the gradient cross product with something else, which is, of course, should be a vector field. So here we still have this vector field F in the Cartesian coordinate. So the curl of F can be calculated by, this is the gradient cross with this F in the Cartesian coordinate. So you know the cross product is like we have ijk, and then we have the first vector, which is the gradient. So we have the x-axis component, y-axis component, z-axis component to be here, here, and here. So we have partial x, partial y, partial z. And we also have the second vector field, which is fx, fy, fz, to be placed here and here and here. So this is the determinant. I'm not sure whether you have learned it yet, but actually in Chinese it is called 行列式. Yeah, so this is a determinant. If you, so this is a 3 times 3 determinant. When you would really like to expand this one, you would have totally 6 terms, which is this one time, this one time, this one, and then plus this one time, this one time, this one. And also you have this one time, this one time, this one, with the plus sign, So you have I partial y fz, which is I partial y fz. So this is the first term. And then you have j partial z fx, j partial z fx. So this is the first one, the second one, and then the third one, k partial x fy, k partial x fy. So this is the third term. First, second, and third mean this is the first. This is the first. This is the second, and this is the third one with the plus sign, because we draw this one from the top left to the bottom right. So this is the first one, the second one, and the third one. And you also have the 3 other terms. The first one is like you draw it like this: I partial z fy, I partial z fy. So this is I partial z fy, but we are drawing this line in another direction, so we have a negative sign here. So this is the fourth one, and then we have j partial x fz. So we have j partial x fz. So this is the 5th term, and finally we have this k partial y fx. So we have this is the last term, k partial y fx. So this is how we would like to expand the determinant, the 3 times 3 determinant, into 6 terms like this. So this is how we would like to calculate the curl in the Cartesian domain. Okay, so for the physical meaning for the curl, suppose we can see this vector field fyz, fxyz. So of course this is the x-axis, this is the y-axis, and we have the vector field as y I hat minus x j hat in the xyz. So it is nothing to do with the z, so we can only draw it on the plane. We don't need to draw a 3D graph for simplicity. And if you want to know, for example, for the original point, it is 0, 0. So you just plug in 0, 0 here. So in the middle is 0. So you cannot see an arrow here. And for example, if it is just say this point is 4, 0. So you plug in 4. X is 4, y is 0. So we have minus 4j, which means that for this point, it points to the negative y direction. So you can see here, this vector points to the negative y direction. Or for example, this point is just now I mentioned that this is 4, 0. So we plug in 4, 0 here. So this is minus 4j. And for example, this point is 0, 4. So we plug in 0, 4 here. So it will be 4i. 4i means point to the positive x direction, which means that we can see here, this one is point to the positive x direction. And you can simply imagine that if it is farther from the original point, then the vector will be longer. So you can see this vector field is actually this one. Can be written as a simple formula. And if we try to calculate the curl of f using this formula, it will be nothing but minus 2k. Minus 2k. You just need to plug in this one into here. You just have fx equals y, fy equals negative x. So here we have fx equals y, fy equals negative x, fz equals 0. You can plug this 3 value into here and calculate out. You can find that it should be minus 2k hat. This means that if this is the rotational axis, you can simply imagine that you can use the right-hand rule here. You use the finger follow the direction of the arrow, and then your finger will point into the page. Yeah, which means that your thumb will point into the page if your finger follow the direction of the arrow. In this case, this is the rotational axis. This is the rotational axis, which is the negative z direction, because k hat is the unit vector in z direction. And you can see that the x direction is this side. This is the x-axis. This is the y-axis, which means that for the positive z-axis, it should follow the right-hand rule, which means that x plus y pointing out of the page is the positive z-axis. And you can see the rotation axis is pointing into the page, which is this one. So this negative 2 means this is the negative direction of this k hat, which means it is rotating clockwise. If you don't ever try to draw this vector field out, even if you only have this one, you can just calculate the curl of this vector field. You'll find that minus k hat is the rotational axis. And then you can use the right-hand rule to simply imagine how the vector field act like. So only according to this one, you can feel that it is rotating clockwise and along the z-axis. Okay, so this is some definition for the divergence and the curl. And here we will introduce 2 theorems. One is called the divergence theorem, also known as the Gauss theorem. So for the Gauss theorem, it is, so the description is like, for f is a vector field, it should satisfy this equation, which means that this is a surface integral. It should be equal to the divergence of this vector field in this triple integral. So it's like over this space you have f. F is the vector field, And of course, you should define the Gaussian surface. For example, this one is the Gaussian surface. Maybe we can call it S. And this is the volume inside this Gaussian surface. We call it V. So some mathematics textbook, we will explicitly write this is for V and this is for S. This is a Gaussian surface. And then the surface for this integral is actually this S surface. And the volume for this triple integral refer to this volume V. And here we define the V, which is inside this Gaussian surface S. So in this case, it means that we can calculate the divergence of this vector field. And then we try to integrate it over this volume. And this one is equal to, we calculate the surface integral directly. We calculate the surface integral directly over this surface. And actually the volume is bounded by this surface S. So it's like, maybe we need to find the triple integral. You don't really like to calculate the triple integral. So you try to see what is the divergence of this one, and then you can just calculate the double integral of this vector field rather than calculating this triple integral, or the other way around. So it is something like you convert a triple integral into a double integral. So the surface integral of a vector field over the boundary of the volume equals the volume integral of the divergence of the vector field over that volume. So if you're interested, you may check this link to see the proof of this theorem. It may take a few pages to really prove this one. I'm not sure whether this link still works because I found it in 2 years ago. Yeah. But yeah, actually you can still find some other way to see the proof. But actually it may be quite difficult to understand, but if you're interested, you can try to see. And the other one is called the Stokes theorem. The Stokes theorem try to link between the line integral and the surface integral. But rather than taking the divergence here, we try to take the curl here. We take the curl and then take the surface integral. This should be equal to the line integral of this one. So the line integral is actually for this path. In this figure, it's called rho round sigma. Round sigma. And and this one is the sigma. Yeah, so this double integral is calculated over this surface, the surface. And this line integral is, of course, calculating over this closed path. So here it means that the line integral of the vector field over the boundary of the surface equals the surface integral of the curl of the vector field over that surface. So this is the description for these two theorems. And in other sense, you can also imagine like this. So this is the divergence theorem. If you consider the physical meaning for the divergence, it is like, or something is going out from a point, the vector field is going out from a point. So it's like you try to see whether this point, the vector field is going out or going in. You calculate all these things over the whole space. You try to calculate all the divergence over the whole volume, because you can see here, you calculate the divergence and you're integrating over the whole volume. And you find out that, for example, at this point, for the point a little bit upper and for a point a little bit lower, if it is going out and going out, so this is just the opposite direction to this one. So these two will be canceled. these two vectors will be cancelled. These two vectors will be cancelled. And maybe if you consider a point just next to it, you will still find the same situation, which is like the adjacent vector will tend to cancel each other. So finally, when you try to calculate the divergence over the whole volume and then you integrate over the volume, then actually what you really do is actually calculating the surface integral, because only the surface cannot be cancelled by some other else. So it turns out this one you're integrating over the whole volume, and then only the surface integral remains. So this is so this is a physical interpretation for this divergence theorem. And for this one, it is even more weird, because calculating this curl is like you try to see whether the vector field is rotating over a point. So it is like, sorry. So it is like you try to see whether the vector field is rotating over the surface. Over the surface, you try to see whether all the points the vector field are rotating. So it is like you calculate all the curl and then you try to track all this curl over the surface. So you will see for this one and this one, if it is rotating clockwise, so this one will be point to the right, this will point to the left. So in between they will cancel. And then finally, it turns out that only the boundary cannot be cancelled by each other. So it turns out that you calculate the curl and then you integrating over the surface, turns out to be the line integral, because only the line integral cannot be cancelled by each other. All the inside part are cancelled. So it's like you change the triple integral and then you find out that all the inside part are cancelled, only the surface integral remain. And here, for this surface integral, you calculate all the curl and then it turns out that only the line integral remain. So you turn a double integral into a line integral. And in other sense, it is called the fundamental theorem of calculus. Fundamental theorem of calculus. Yeah, when you learn the calculus, you know that there is a theorem called the fundamental theorem of calculus in one dimension. It is like if let's say partial df dx is small f, then we will have integration of f dx from a to x is like f of x minus f of a, something like that. So this is called the fundamental theorem. It tries to link the derivative with the integration. So this is something like the fundamental theorem, but in 2 dimensions or even 3 dimensions. So the fundamental theorem you learn in the calculus class is the 1D version. So this is the 2D version, and this is the 3D version for the fundamental theorem of calculus.